Okay, we ready? Okay. All right, my name is Brandon Larson, and I'm going to be talking about concrete for construction on Mars. First, a little background. Biggest problem we have doing anything on Mars is the cost of getting cargo there. Elon Musk says he can get a metric ton of cargo there for 140 to 190 million, which right now is our cheapest option available. So the only way we're going to be able to build anything there is in situ resource utilization, using what we find there on site. And one resource we can see right there in front of us, sand and gravel all over the place. And as we all know, all you have to do is add some cement to sand and gravel and you get concrete, which we've been using for 2,000 years to build things. So the obvious solution is to bring a cement factory and a steel mill to Mars. And, there's my steel mill. Okay, but there's some problems with that. The Portland cement we use here on Earth won't work on Mars for a lot of reasons. One is it requires water to remain liquid for a long time, several weeks. And in the Martian atmosphere, it'll evaporate very quickly, and it'll also boil. Because the Martian atmosphere is almost always below the triple point of water. And it also takes a lot of energy to produce it at very high temperatures from the raw materials available. There's another option, magnesium oxychloride cement. It's a magnesium-based cement composed of magnesium oxide, a powder here, magnesium chloride, a very common type of salt, and of course, plain old water. And the advantage is that the water in here, while it does require water to cure, the water is mixed in with the magnesium chloride salt in a dense brine, which will not boil at Martian atmospheric pressure. It sets up and cures in less than a day, after which the water is locked up in the crystal structure and will not evaporate. And it's stronger and more durable than Portland cement concrete. Another advantage is it takes less energy to produce it than Portland cement concrete, and energy will be a very scarce resource on Mars. And the raw materials to produce it have been found on Mars. So it's stronger, faster curing, and easy to produce. So in order to test it for use on Mars, first, well, let me explain that it's not normally used for construction here on Earth because while it does have a lot of advantages, its main disadvantage is it does not resist water very well, which is a big problem here on Earth, but not such a concern on Mars. So I had to come up with a structural concrete mix by trial and error. And here you can see some of my early trials, trying to come up with something that would work. And this is the mix that I came up with. Not ideal, not optimal, but good enough to form a solid concrete for testing. And testing it after 1 week of curing, got a final compressive strength of 8,853 pounds per square inch of force. Should explain compression testing is just crushing. We make concrete cylinders like I have up here and put it in a compression tester and just crush it and apply pressure until it fails. And I did flexural strength testing on these beams here and got good flexural strength, 1,070 pounds per square inch. The way that works is to support the beams at the end, apply a load in the center till it breaks. Interesting thing about this cement is that while with Portland cement concrete, once it starts to crack, that crack propagates all the way through and it fails completely. With this, the beams didn't fail completely. These beams shown here are shown after failure, and you can just barely see there's a crack up the middle extending about halfway through the beam. After failure, there was still enough strength left in the beam to support my entire weight. So that's another big advantage of it. And I also did direct tensile testing, pulling a sample apart, and got very good and consistent tensile strength with it of nearly 1,000 pounds per square inch. And well, this thing's very heavy. Yes, it is. It's about, I think some people would even have trouble lifting it.
We'll keep that at the Mars Foundation table.
Yeah, you can come and look at it if you want. It'll be out.
How does this compare with concrete?
With Portland cement concrete, it's about double the strength you would expect. And with Portland cement concrete, the tensile strength it's comparable but not as reliable. The variation in tensile strength would be much greater. With this, the tensile strength is much more consistent, which offers a potential of building pressurized structures without tensile reinforcement, which would be a big advantage, greatly simplifying construction. So I had to see if it would work in the Martian atmosphere. I built this equipment to test it at Martian atmospheric pressure. It's just a bell jar type vacuum chamber in a beverage cooler used to regulate temperature, and there's just a basic vacuum pump and a pressurized air tank for a vacuum reservoir with a solenoid valve and Pirani pressure gauge for pressure control. It's a type of absolute pressure gauge. It's a special type of gauge. Very expensive, by the way. So here are my samples in the vacuum chamber at 6 millibars. One problem I had was with dissolved gases that were in the brine and the mixed cement. Since I wasn't able to vibrate the samples to get rid of the air bubbles, I just had to live with the air bubbles. And you can see it bubbling and foaming up, not from boiling, but from dissolved gases. And these are the final samples. This was an earlier trial. The final trials, yeah. Okay, these are the samples I did. The samples I used here were 4-inch, a little smaller.
I'm sorry, did you mix it and then put it in the low pressurizer?
Yes, I did.
Did you make it in the low pressurizer?
No, the only way I could do it was to mix it outside and put it in the samples immediately. It was the best I could do.
Mixed it in the Martian atmosphere, it would not have had that same boil-off?
Right. Like I said, if you can vibrate it, we normally use a vibrator to consolidate concrete, and that forces the air bubbles out of there. It also occurs in Portland cement concrete, but I wasn't able to do that with the equipment I had available. So these were the samples, and I had to work around the air bubbles. I'll get to how I did that. This was the final results. I had 3 samples in the vacuum chamber that you can see, and 3 more samples that were cured outside of the chamber at normal atmospheric pressure. So those did not have the air voids. And the final strength of my trials in the chamber were 2,554 psi compressive strength, and the controls were 6,382 psi. Should explain the final strength I had before was after 7 days. This was after 2 days, only 2 days of curing. That's why the control strength is lower. The void volume in the trials in the chamber I calculated it just by the weight of the samples, was 17.3%. I also weighed the samples before I put them in the chamber and then afterwards to measure the water loss due to evaporation, and it was only 9% of the total water in the cement, in the concrete. Now, to account for the strength loss due to the void volume. This is from a concrete design book showing the compressive strength of air-entrained concrete with air voids in it, and the expected strength as a result of the strength loss due to the air voids. At 17.3% void volume, this is based on 4,800 psi of strength at 100% consolidation, 0 void volume. And at that strength, you would expect 2,200 psi, and with the amount of void volume we had. Now, comparing that with the strength of the controls, we would expect to get 2,934 psi with that amount of void volume, and our actual strength is 87% of that. So that which is very close. Shows the concrete did fully cure. Next is, how do you produce it on Mars? Well, the magnesium oxide is the main component and the toughest to produce. It can be produced from direct heating of magnesium hydroxide, a mineral we call brucite, fairly common on Earth. As far as I know, it has not been found on Mars yet, but with all the other hydrated minerals we've found on Mars, there's a good chance we'll find it. The most common source here on Earth is magnesium carbonate, which has been discovered on Mars and should be fairly easy to find there. And it can also be produced from magnesium sulfate, which has been found in large quantities on Mars. But it would either take a much greater energy input for direct reduction, direct decomposition, or it can be put into solution and we can precipitate magnesium hydroxide out of that solution to produce magnesium oxide with a much smaller energy input. Now, the magnesium chloride should be fairly easy to find in the salt deposits that have been found on Mars. Here on Earth, it's produced by separating it out of salt deposits or even seawater. Now, some magnesium sulfate is also a minor ingredient that's been shown in some studies to improve the durability at the expense of a slight reduction in strength. And that's something I'm investigating further. Now, as far as the energy required, if we can find usable quantities of, well, I got these figures switched out. Sorry about that. Magnesite, the most common mineral, the energy requirement is 5.45 million megawatt hours per ton of magnesium oxide. I got these two numbers switched. Now, if to produce it from brucite, it would be 2.81 megawatt hours per ton. Now, where I got those numbers was the energy required to heat the material and then the energy required for thermal decomposition, assuming 50% thermal efficiency. So I took that figure and just doubled it, just as a rough estimate. Now, if we wanted to produce it from magnesium sulfate by direct thermal decomposition, it would take over 10 million watt hours per ton, more than double that of magnesite. And a byproduct of that is sulfur dioxide and sulfur trioxide, which would present problems with exposure to the equipment, since that's, when combined with water, produces sulfuric acid. So the power supply required, assuming we're using magnesium carbonate as our feedstock, if we have a nuclear power plant or something that can provide constant power around the clock, we would need 20 kilowatt hours of electricity to produce a usable quantity, assuming we're producing 1 ton of it a week, which would be enough to to build a usable structure within a few months. Now, if we're using solar, since it would only be usable for part of the day, we would need 100 kilowatts of capacity rated for Mars, which would be about 220 kilowatt hours of solar rated power here on Earth. And for the reference design I've been working with, which I'll show you later, we'd need the ability to move about 50 cubic meters of regolith per day. And just a rough estimate, we'd need, I'm thinking of, for ore transport, 5 tons of ore per week over a distance of 100 kilometers should be able to provide our transportation needs. And if we end up precipitating, if we need to use precipitation processes, 2 cubic meters precipitation tank capacity should be more than enough. Now, yes, to produce 1 ton of magnesium oxide per week, which would give us about 2 tons of cement. Now, the method of construction I would propose is using inflatable airforms like this, which we use on Earth. This is just an example of an inflatable airform. And there's a structure built from a small house built with airform construction. The way it's built is you inflate the airform and just simply place zero slump or low slump concrete on the outside and let it dry. Then you can, once it's cured, you deflate the airform, peel it off the inside, and reuse it. The advantages of airform construction: the airform itself is lightweight and reusable. For a 30-foot dome, the airform would only weigh about 400 pounds using 400 pounds or less. Very flexible in how you can construct it, since you can, the background here is an example of a building made with an airform. You could place openings wherever you want. You could put an airlock or a hatch wherever just by placing it on the airform and forming concrete around it. And it's used here on Earth in places in remote areas with very little or no industrial infrastructure, like parts of Africa and Central America. And here's an example of airform construction. I believe this is in someplace in Central America, possibly Honduras. The way it's commonly used with Portland cement is the rebar is placed around the airform and then the concrete is placed over that. I'm hoping it's possible to do that because of the properties of this cement, to do it without any tensile reinforcement, hopefully. Now, as far as building on Mars, the first step would be excavating a pit such as this. Then place just a flat foundation at the bottom. Attach the airform to the foundation and inflate it like this. Then we start placing the concrete around the airform like this, like you can see here. And start building it up in layers. Then we fill in the crater, add more concrete and keep going. And this is one possible habitat, the finished product, what we could expect it to look like and because we're talking about building pressurized structures out of it, we're not dependent on the weight of the Martian soil on top of it to counteract the pressure inside. So we can go ahead and build airlocks on the surface for access to the structure down below. And what else? So that's now I I'd like to thank Ron Voigt from Forever Board. He donated the magnesium oxide that I used in my studies. And Mark Shand of Premier Chemical. He's done a lot of research on magnesium oxide production and use and gave me some advice on how to work with this material. So, do we have any questions? Yes.
The concrete on these inflatable things is usually pumped on.
Yes.
Correct.
Typically shotcrete.
Still work in Cosmos.
It could, but, well, they typically use shotcrete, which, oh, the question was the concrete is typically pumped or sprayed on. It's called shotcrete. You basically take the concrete and just spray it out of a nozzle onto the airform. One problem is that you get a lot of wasted material, a lot of the gravel bounces off, and it's very unreliable. It's fine if you're just building a simple compressive structure with reinforcement, but what I'm thinking of for this construction is pumping it into place and using a vibrating, like a kind of vibrating trowel to vibrate it and shape it against the airform. And you'll see on there, I showed the concrete placed in bands around that. The reason for that is in a structure like this under tension, the greatest stress is going to be the hoop stress around the cylinder, which is going to be twice as much as the longitudinal stress in the cylinder and the tensile stress, the membrane stress in the dome at the top. So since you don't, by minimizing the concrete joints in that hoop, in that circumference, you get better strength, better reliability. Yes?
A couple of speakers have talked about the fact that they seem to have a pretty good conviction that there are a lot of caves on Mars.
Yes.
With the habitat.
Yes.
Have you thought about using this system in conjunction with caves?
Absolutely. It would work just fine for, one thing I found out is this type of cement sticks to a lot of materials very well. In fact, I had to throw out a few stainless steel pots and tools because I couldn't get the stuff off of there. And yeah, it sticks to just about anything. And it'd be great for sealing up caves and lava tubes. Yes. That would make habitat construction far easier. Yes?
Why did you start doing this project? Is it because of interest in Mars, or?
Well, I was interested when I was younger, but when I saw NASA not going anywhere, then I saw the new space companies about 10 to 15 years ago dropping off the radar one by one, I just kind of lost interest. But when I saw what Elon Musk was doing and saw the things might actually go somewhere, I decided I actually needed one unit in my last semester as an undergrad to fill out, and I was talking with Dr. Nash, my advisor, about doing something related to concrete construction on Mars, and he gave me a book on concrete technology that had a little blurb about magnesium oxychloride cement. So I just looked into it and thought, hey, this might work. So one very busy semester and over $5,000 later, I came out with this. Yes?
I just wanted to say that Brandon and I are very interested in building one of these. So I see you, Brandon, or myself, and this is David Nash, Untitled Chapter, is the advisor. So that's all.
Yes, in the back.
Wouldn't more blocks be similar?
That's what I thought. I looked at a few different construction methods, and at first I did have grouted masonry in mind. I was thinking just building concrete blocks, assembling them, and then filling them out. I even worked on a concrete masonry unit design, but then I figured you would need, just for the stem wall, several thousand blocks, and then trying to do that with a dome would greatly complicate things. Well, I found out about airform construction and realized that would be far simpler, and you wouldn't need all the equipment to produce thousands of, because you need a lot of molds. You're going to need molding equipment, and here it's just a big fabric bag weighing a few hundred pounds. That's your formwork. Yes, in the back.
I've seen some videos of machines that form curves in whatever shape you want.
Right.
And I'm thinking that, you could easily form a curve and then another curve on top of that, develop for, modify that kind of equipment to do the kind of thing you're talking about.
Yes. Well, the thing to keep in mind is it still takes at least half a day to a full day to cure, so you have to have it held in place by the formwork. It'll stay in place up against the formwork, but you still need it there to hold it in place while it's curing. But that might be an option, though. Have any other questions? Yes, in the red.
What is the viscosity of it compared to Portland cement?
Well, just like Portland cement, it depends. The way you do it normally is when you're mixing it, you figure out what viscosity you need. It's called slump. There's a slump test where you design for the viscosity you need. And for this, since we're placing it on an airform and it's not completely contained, you need what's called zero slump or low slump concrete. So you can just push it up against the airform and leave it there and it'll stay in place. But if we had molds or something like that, we could always mix it with greater viscosity so it'll flow into the mold. You just design for whatever you need. Yes?
How stable is the structure you chose to any sort of seismic stress?
Well, since I didn't really consider seismic stress because, well, we haven't found any evidence of earthquakes on Mars, and as far as we know, the crust is much thicker and not very active.
There was a Mars quake detected recently, I recall, on MRO.
Really? I hadn't heard about that.
Yeah, that was an orbiter that detected it. I can't remember quite what this was detected recently, so
Oh.
some testing stuff.
Oh, okay. I'll have to look at that, but okay. Yes, in the back.
How do you deal with very, very, very cold temperatures?
Well, this is very sensitive to temperature. It needs to be about 10 to 25 degrees centigrade. Yeah. So you would have to make sure that the material was warm enough that it would cure. I did try it at low temperatures, and below 10 degrees centigrade, it just won't set up. So, but solar reflectors are an option, just direct solar heating. And because the Martian atmosphere is so thin, you're really only dealing with radiative losses. So that should be easy to do with solar reflectors.
Let me address that. You can also hang a reflective mylar tent over it in the air so thin that it'll hold a lot of heat in, at least temporarily.
Okay, yes, in the,
Does that generate heat like concrete does?
yes it does. It gets very warm.
You're more likely to have to add a little bit. You may need to cool or put a fan on it.
Not really, because it doesn't get really hot, maybe a little over 100 degrees Fahrenheit. But when it does it only does that when it's already solid. When it's getting solid, and so I don't really see that being a big concern. It's not enough to damage the formwork or to cause any boiling problems because it's already solidified by the time it starts generating a lot of heat. Yes, in the back.
How resilient is it to temperature swings after it's cured?
I've found one study of a mix similar to what I'm using, and they did test it in thermal cycling, and it responded very well. It didn't, and I still have a lot of testing to do, but I am going to be doing freeze and thaw testing from around -15 to 40 degrees centigrade to test that. Anyone else?
Any more questions? I think
Yes.
I'm just curious whether or not there's any thing about having regular atmosphere contact with this. Is there off-gassing, or is there any sort of deterioration that happens?
Not really. I mean, for the most part, it behaves a lot like conventional concrete. It just solidifies, and that's it. And from what I calculated, with this reference design I've got, that's I think a 32 diameter, a dome with 32 feet in diameter with a 16-foot high stem wall. I calculated that you could build with an 8-inch thick shell. You could pressurize that to 10 psi and still have a safety factor of 3 for the tensile strength of the concrete. And if you'd like to know more, there's my email address. You can email me with any other questions you might have.